Okay, thank you. Okay. Hello. Yeah. Okay. Now I can talk about what I was gonna. Yeah, this is what I prepared today. So this is the difference between that and me rambling about cubic equations. So today we're gonna work with states. I know maybe a few of you have seen states before. I don't know if I'm gonna be able to like set up a poll or something, and I'm probably just not going to do that. But states are like a sort of like, how do I put this? They are a combinatorial construct. So the general gist of it is like you have a bunch of points, right? And you can have like, you can think of it as like a frog or something. And you know, this frog, you know, goes different places with different probabilities, and the probabilities are fixed or maybe they're varying. I mean, it doesn't, the overall idea is that it's sort of a random walk in some set of points, and you want to sort of control, you want to find, be able to solve for the probability that, you know, it gets here at a certain time or gets here after an even number of turns, or the expected value of times it does this after something, or given some condition, right? Just very, very vaguely speaking, something walks around a few nodes and they're connected some way, like, oh, this is like, you know, 2/3 probability, you go here, and like a 1/3 probability, you go here, or something, right? And so like very vaguely speaking, you sort of just move around randomly, and sort of some fixed probability anyways, you have some control over that. So I don't know what happened, but okay. Wait, oh, I'm doing Zoom annotation. That's not what I intended. Okay. Goodbye. I'm going to clear that. But I was trying to do this. Okay. So then there's this like theorem, I guess. I don't like phrasing things as theorems, generally speaking, when I like try to explain them to people, because I think that sometimes theorems give problems too much credit for being smart, and this is not that smart, right? Theorem is like, oh yeah, I spent so much time working on this and thinking about it and, you know, mulling it over or something. And this is not really that. This is just like sort of the heuristic that we work with. So it means that basically, like, let's say there's a given probability that we win at a given node. Like, say, you know, when you're at this position, then there's some probability you're going to win. Then the probability you win at this point is just like, if there's like, you know, a bunch of probabilities here going out, you know, and there's more probabilities you're going to win here, like, you know, x1, x2, x3, then like your probability that you win here is just this, right? And like, this makes sense. Like, if you're going to win here, then like, if you're going to win here, then you have to go to one of these, right? And you go to one of these with the given probability, you have some fixed probability. And so these are all vague ideas. But this is definitely very confusing. This is definitely very confusing because I am speaking in abstract terms. And so you probably don't know what the hell I'm talking about. Anyways, you probably don't know what the heck I'm talking about. And so I'll give an example. So a basic example. And so, yeah, Anastasia and Anastasia are playing a tennis match. Both players start at 0 points. And the first player to get 2 more points than the other player wins the whole match. And Anastasia wins with probability 4/7. Find the probability that Anastasia wins the whole tennis match. So we have some states, right? Again, we're rooting for Anastasia. This is an important concept. We are trying to find the probability that Anastasia wins. Now, like, obviously this doesn't really mean that much mathematically, but it's like an interesting, it's a better way to sort of phrase and sort of sanity check your results, right? Like, for example, you know that Anastasia has a higher chance of winning than Bananastasia. It would be very weird otherwise, right? And so, like, because scoring points is good, right? So that's one of those things. So then, of course, you could like set up like an infinitely large grid. I mean, like, I maybe this is a mistake people make. I don't think it is, but maybe people do this. Like, you can set up an infinitely large grid. And you say, oh, there's a probability you win here, and there's a probability you win here, and there's a probability you win here, and it's really complicated, right? But like, an important thing to notice is that when you have, and I suspect this is probably, I'm gonna stop this. That an important thing to notice is that it doesn't really matter what your exact score is, right? Like, it doesn't matter if it's like 0/0 or like 2021, 2021. It just matters what the difference is. And so instead of our states being, you know, an infinite grid of points, they're actually just 3, right? So, you know, Anastasia equals Bananastasia, like A equals B maybe. And then this is like, you know, A plus 1, and this is A minus 1. And so, you know, there's a 4/7 probability this goes, and there's a 4/7 probability this goes. Okay. Can I zoom in? I think I can. Yeah, I can. Wow. Okay, nice. No, it's not. I'm trying to scroll. Can I scroll over, or is that not going to happen? That worked out. Yes, yes. I answered this somehow. I don't know how to click this. But anyways, yeah. So okay. That's enough. So there's sort of a 4/7 probability that we move sort of onwards, right, in the sort of the good direction. And not all states problems, of course, have a very obvious good direction, but this one does. So we do this, we do this. And so the probability we win, right, is this probability, right? The probability that we win when they start the same school. Yes, both players start at 0 points, right? And so we can give these variable names. This is I don't know. This is like I'm gonna do x1, x2, x3. I know people like maybe like PQR or XYZ, but I think that it is a good habit to make all of the variables of the same type, the same like the same letter. This is because you may not be able to understand what like Y and Z are, and like sometimes it's confusing. So I would not. Sometimes you have to, or sometimes there's like a good reason for it. But since these are vaguely of the same type, right? They're like, oh, probability you win after you're up some amount of points, then yeah, you probably just do this. And so x2 equals 4/7 of x3 plus 3/7 of x1, which is sort of what we were talking about earlier with that theorem, right? But again, it is more of a heuristic. It's like I'm thinking, hey, the probability I win here is the probability that after I move, I win there, or after I move, then I win there, or whatever, right? And similarly, then x3 is 4/7 plus 3/7 x2, and x1 equals 4/7 x2. And so you can substitute stuff around. Get like x2 equals 4/7 x3 plus 12/49 of x2. Then you get something horrendous. You get like, not 20, 37/49 x2 equals 4/7 x3. And so, x3 equals like 28/37. No. Sorry. X3 equals 37/28 x2, right? And you'll find you'll get a lot of equations of this form, by the way, like when you're doing states, especially if you're working from the losing end, right? Which is where I started with x1, right? And then finally, you can substitute stuff in, and you get like 25/28 x2 equals 4/7. And I know my handwriting is getting bad, but x2 equals 16/25, which sounds about right. I don't actually know if this is the right answer, but again, this is just a sample problem just to get the idea started. And if the answer is wrong, I am very, very sorry. But I don't think it is. All right. So of course, I think that this basic idea is not too hard to understand, right? Like, and you could probably solve a lot of problems of that form. Like, oh, Anastasia wins if she is 3 points ahead, but Anastasia only needs to be 2 points ahead. Who wins now? And now there's like, maybe the unbalance, or maybe Anastasia actually has a high chance of winning, or something. But those kinds of problems are generally the same type. But sometimes you're going to have to work with a lot of stuff. And I realized I did not give myself that much space for this problem, but it's okay because I suspect it, because I know how to do it. It shouldn't be too bad. So a rook is on a chessboard, and I am not going to draw the whole chessboard. Never do this. Like very rarely are you going to need the whole 8x8 structure of the chessboard. That's 64 squares. Don't worry about all 64 squares. There are too many squares. And I don't know any chess, but I know that A8 is here. That's all that really matters to me. And so we start, at A1. And the rook randomly moves to a different square, either in the same row or in the same column. Basically, just makes a random move, right? And so the rook continues to move until it arrives at a square in either row 8 or column H. Basically, again, this sort of, maybe I should make this a different color. But like, say that, oh, crap. Okay. No, okay, no. No. Can I actually color this? I'm gonna make it orange. Orange is a good color. Okay, and so we realize that there's a lot of symmetry, right? Off the bat, we don't really care if it's like B2, like we don't care if it's B8, C8, or whatever, H8, right? And in fact, when we start anywhere, there's sort of like like the probability when you're starting here, there are only two special ones, right? There's A8, there's, H1, and all of these ones are basically the same, right? Like in your eyes, right? And so actually, this is not a hard states problem at all, and I'm running out of space. I will use this space down here and then I'll delete it later. Sorry. Again, I don't know if I am being friendly to notes takers because I am not a notes taker, but if that's a problem, let me know. I don't want to make it hard for you. So in any case, there's a probability, there's a probability of, and I don't think that there's a very clear states diagram here, by the way, but that's because I think it is worse to do it as a states diagram otherwise. So there's a probability of, stuff in your row, right? Which is like, we call this probability like Q, right? So we call this probability P, right? Stuff in your row. So for example, for this point, then that's A8 or H1, right? And then there's Q, which is one minus P, is the probability of going somewhere else, right? And so this is a little bit funky, but given our random movement, we go, a random place, then we have a 2/7 chance, not 2/7 chance, we have a 1/7 chance of instantly winning from here, right? We instantly are happy, right? By the way, this is P, right? And otherwise, then we have, okay, actually, no, it is actually smarter to have states though. Oops. Well, it might not be necessary. Yeah, I don't think it's necessary. It's not necessary. Okay, so then we have a ones, actually, okay. There's one thing I will do here, and I will make I'll make these two separate because they're the same. The probability ends at A is the same as the probability ends at H1, again by symmetry reasons. But I will split those into two parts, and so like, okay. This ended up being very awkward. So there's a 1/14th chance we instantly win at A8, right? We instantly go here and we are happy, right? And so, okay, P is now the probability that you go to like the top, like the probability that you end up at the same column as the one you are in now. So the 1/14th chance that happens, there's a 6/14th or 3/7 chance that you end up in the same row, right? Times P. And then there is another probability. There is a 1/2 chance that you just end up in a different row altogether, right? And so then you have a 1 minus P, well, not quite. You have something like a 1 minus 2P chance, right? And then that's divided by all of these. So there are, and this is super vague, but something like this. Oops, this was not all planned out. And you can solve this. That's the sort of like very, very exploiting symmetry idea here. It's basically that like it doesn't matter, like these are all the same in your eyes and these two are all the same in your eyes. But I kind of, again, I want to avoid working out too much algebra. I will work out algebra for like some of the examples, but some of the examples I don't think it's that instructive. Especially if the algebra is kind of bad, or like it gets me numbers that are so big that I'm like, is it worth working out? I usually am a proponent of like, actually do your own algebra, but in this scenario, I think that this problem is more trying to illustrate that the ones in the same row or the same column are the same. The ones in a different row and a different column, sort of, then these ones are all the same as well, in some sense, right? Because we don't really care, like any permutation of the rows or any permutation of the columns, then that should be fine, right? Generally speaking. So I'm just going to work on the next one because this next one is probably easier to sort of visualize. That other one was just sort of a way to sort of explain an idea. But if you have a question, like still ask me about that. Like you want me to ask about the previous question, then I can try to explain like what I was saying in more detail. But like that's fine with me. Like I don't think that it helps if I am just saying things that are bouncing off. But I will try to move on if possible. If you have questions, please let me know. Like there are not really dumb questions as much as there are people who are too, I won't say dumb, but too worried to ask questions. Okay, so this problem, there is a small pond with 11 lily pads in a row labeled 0 through 10. Do not draw all the lily pads. There are too many lily pads. There are 10 of them and you do not need to draw any of them. So the first thing we know is that this condition, like it goes to n minus 1 with probability n over 10. It goes to n plus 1 with probability 1 minus n over 10, right? And if it gets 0, it dies. If it goes to 0, if it goes to 10, then it leaves and it wins, right? And so that's our quote unquote win condition. And so what do we know about pad 5? What is the probability at pad 5? I guess this is the symmetry here, which is the question I'm asking. Like, what is the probability that the frog wins at pad 5? This is a question, actually. I would like you to answer it, if possible. I understand if you can't, but and if you're lost, let me know. I lost a lot of people. I'm gonna stick another combo guy. Okay. Well, no one answered the question. That's really bad. But the probability you went at pad 5, which is in the middle, right? We have a bunch of pads over here. We have a bunch of pads over here. This is symmetric, right? You go here with probability 1/2, you go here with probability 1/2, and you go here with probability, 0.6, go here with probability 0.4, 0.4. So the whole idea is that pad 5, the whole thing is symmetric about pad 5. So the probability you win at pad 5 is exactly 1/2 because of symmetry. And that's really all that matters. Again, I don't really want to do too much algebra. So I will just say that the algebra for this one is pretty bad. Like you get like a 146 somewhere. It's not a nice number. But it helps a lot, right? It helps a lot to have 1/2 here instead of having to get all the way to 1 over here, right? Which is what like sort of winning is. Winning is like a probability of 1. Right? And so that's this problem. Again, I don't want to go too much into the computational details. But this one I will go to the computational details because I have space and also because this is an AIME number 13. I think that's important. Okay, this problem is hard. This problem is really, really hard. So this is what I would call a problem that is like even for like AIME last 5 standards, a pretty hard one. Now, there are people who will say that this problem is actually very easy because you can get the answer. Oh yeah, sorry. This problem, I did not completely solve it. But, what do you what do you want to know, or like what do you need help with? Right. So like the idea is that it's symmetric about 5, and then you can just do the same states like battery stuff, the probability and stuff. Yeah, it's a shame because if I like actually draw diagrams before, that would even be better, but I didn't do that. So unfortunately, okay. This problem is really hard, but we're gonna do it because we can talk about states here. And anyways, as I was saying, some people thought this one was really easy because you can like get the answer in a sort of fakey way. But I think that those solutions are very non-rigorous and kind of confusing. They're kind of scary, and I don't really think that they make much sense. But like the vague idea is like, oh, well, you can just treat it as a single dice roll with probability 1 over 216, and you get the answer very quickly. But yeah, you can see why you might be able to see why I was kind of skeptical of things like that. I took this test. God, I'm so old. Anyways, so there are so many probabilities here. There are a lot of states. First of all, we care about the parity. We care about the parity. 1 odd is a state. 1 even is a state. 2 odd is a state. 2 even is a state. 3 odd. Well, sorry, not 2. When I say 2, I mean 1 to 2, right? Like 1, 2. And then sorry, there's nothing odd. This is just like some bad number, right? Like for example, if you end with 6 or something, that is just like bad. Like if your most recent roll is 6, then that's a useless roll, and you basically might have no rolls at all, right? And then there's like win. Like this is win, and this is lose, right? Vaguely speaking, like this is win, this is lose. And so the first important observation is that the probability that you win on even is the same as the probability that you lose on odd. And that allows you to say, hey, guess what? This is P and this is 1 minus P, and then we're done. We don't need to worry about that anymore. And that's good for the future. But for now, we are going to, but I need to explain why this is true. So winning on even is the same as losing on odd, in the sense that if you were to do a series of rolls that win on even, then that exact series of rolls would lose on odd, because winning is dependent on the parity of the first 1, 2, 3. We know that we're going to get 1, 2, 3 eventually, right? Like sort of, this just happens. But it's about the parity, right? The parity of the 1, 2, 3. If it's even, then there's that, and then if it's odd, there's that. But if you start with even and you get odd, that's the probability. That's what probability we care about, right? If we start with even and we get odd, that's the same as starting with odd and getting even, right? That's the same set of rolls will get you the same stuff, and so you can sort of treat it as a bijection, a one-to-one correspondence, sets of the same size, probabilities are the same. So winning on even is the same as losing on odd. That's the first important observation, right? And that allows you to sort of just really, really instantly draw this diagram, which is important. And this is like, I'm doing P and Q here because these are not really in any sequential order. So, or not necessarily, they are in a sequential order, but they're not like, they don't represent numbers. They don't represent like -1, 0, 1 or something. And so now we just need to draw out all the annoying states arrows. First of all, if you have nothing and you draw nothing again with a probability like 5/6, right? Then you just like draw nothing. Oops, right? And then if you draw 1, then you're happy and you get to go further. You get to go, to here. Obviously, if you roll and you're currently started with an even number of rolls and you roll once, then you go to an odd number of rolls. Not go to an even number of rolls, right? And so that's 1/6 here. And same thing here. It's, of course, this is also symmetric, by the way. And if you start with 1, if you already have a 1 in the bank, if you get a 2, then look at that, you're happy, right? If you get another 1, then you also get, this, you're fine here with another 1/6 chance. And you have a 4th, 6th chance to be sad, and you'll go all the way back to the start, right? And again, I realize this is cluttered. Try to draw something else, something on your own paper, but right. And so again, same thing. You can do this backwards as well. 1/6, 1/6, 4/6. I realize this is getting quite cluttered. Maybe I'll just draw a bigger diagram. I have time to draw a bigger diagram. That's a good idea. We're gonna erase everything, which is really bad, but so we're gonna draw a bigger diagram because I realized that the previous one was not really successful. So this is nothing. This is nothing. This is odd. This is even. This is 1 odd, 1 even, 1, 2 odd, and this is 1, 2 even, win, lose. All right, and so what we have is that we, 5/6 here, and I'm just gonna draw an arrow like this. This is not good notation, but 4/6 here, 1/6, 4/6, 1/6, and this goes to this is 1/6. And that's both ways. Then here, if we have 1, 2, and we get another 1, we're back here again. If we get a 3, we win, we're happy. And we can also, again, go all the way back to the start. And here, same thing. We can go here, with 1/6. Oh, wait, I want to talk about this. Oops. Right. So this also goes here with 1/6. And then this one, same idea. It's symmetric again. You can go here, you can go here, and you can win, right? And generally speaking, going back to the start is 4/6. Going back to 1 is 1/6, and going onwards is 1/6. Other than the starting one, where you don't go to, there's no onwards anymore. When you're here, onwards and going to 1 are the same thing. Anyways, we explained that this is P, this is 1 minus P, this is Q, this is 1 minus Q, this is R, this is 1 minus R. And so we have the equations P equals 5/6 P plus, sorry, 5/6 of 1 minus p plus 1/6 of 1 minus q. We have q equals 4/6 of 1 minus p plus, 1/6 of 1 minus q plus 1/6 of 1 minus r. And r equals 1/6 chance of just happy plus, 4/6 chance of 1 minus p plus 1/6 chance of 1 minus q. And this is a lot of equations, and that's a lot of equations. And you can solve this. And I will actually try to solve this time because I think that you can probably solve it without too much hassle. In fact, you can note that when you subtract this bottom equation from the top equation, let's do that first, and we get r minus q equals 1/6 minus 1/6 1 minus r, right? And then that's miraculously 1/6 plus 1/6 r. And so q then is just 5/6 r minus 1/6. Or actually, it would probably be better to describe r in terms of q. And so q is, q, r equals q plus 6q plus 1 over 5 r. And so then we can substitute this back in here and we'll get equations again. This time the equations being worse. But I mean, it's not too bad. I will just, I actually have space over here. What am I doing? Yeah, I can draw over here. Okay, that's good. I've been limited to the paper the whole time. I'm overthinking it. Then, okay, 1 minus r. So here we have, q equals 1 minus 4 over 6p plus 1 over 6q minus 1 over 6r. We know that r is this thingy. We divide that by 6 and we get, that's minus, q plus, or 6q plus 1 over 30 is probably the best way to describe it. We add this back over here and we get, q plus 1 over 5q plus 1 over 6q equals 1 minus 4 over 6p minus 1 over 30. And p, or I guess 11 over 6p equals 1 minus 1 over 6q. And you can solve for p now, actually, if you just switch the sides. This thing is, I'm doing things in my head pretty quickly because as much as I said I was going to do calculations, I don't like doing them. And this is 29 over 30 minus 4 over 6p. This is, 11 over 6p. We're going to multiply this entire thing by 41 over 5. Well, not 41, 40 over 55. Actually, no, what am I doing? No, I want this thing. So I want this thing to be multiplied by 41 over 5. Yes, okay. And 45, 1 over 5 on both sides. So then I get, okay, someone raise their hand. What is it? Please put it in the chat or in the Q&A. I don't, obviously I can't talk to you directly. But someone raise their hand and I want to address that. Okay, if it was an accident, it could have been an accident, but I don't want to zoom that. I think you can probably private message me. You can probably use the Q&A tab. But otherwise, yeah, it was an accident. Okay, that's good. So then we're multiplying again, and we get, 41 over 5 minus 41 over 30q equals 451 over 30p. And we add these together, we get some horrendous expression like 41 over 5 minus 29 over 30 equals 431 over 30p. Wow, looks like I'm going to get the right answer. It never happens. This is 246 minus 29. That's 217 over, I believe I'm off by 1. Never mind then. I missed something. No. Well, this is why you don't try to do things really, really quickly. You will drop some stuff. Oh, no, no, no. I messed up here. There is no extra 1/6 here. Yeah, this is just this. Okay, I lost a lot of stuff. So there's no this. There's no 21. There's no 29/30. This is just 1. And so this is just 1. And so that's just, 36/5. Okay, yeah, there we go. And the answer is 216/35 for 31. And this is why some people were able to cheese it. This is like not a hard quote unquote answer to guess. So if you want to know how people cheese it, people cheese it because the answer was like this. And you could probably, and sometimes you'd get it like even fix it with fake. Oh no, I made an error. Okay. Not here. Sorry. This is next section. Next is expected value. I said other uses here. I will not detail the other uses. For just like dumb reasons, I guess. And actually, I forgot about the +1. I can't believe I forgot about the +1. The +1 is very important. Otherwise, we're just doing the same thing. So it's the same idea. When you start at a node, the expected value of the length of the path is when you go here, and then you guess what? You get a +1 length of the path every time you go over here. And the probability you end up here, and then there's some given length. You expect to go so far after you're here. You expect to go so far after you're here. You expect to go so far after here. P1, E1, P2, E2, P3, E3. And so what you get is like P1 times E1 plus 1, right? And that's just, sum of Pi, EI plus 1. That's like algebra, right? That's what we're solving. Again, confusing because I phrased it all as algebra intentionally in the sense that I want to make it clear that algebra is not always is the best way to put things on paper, but is the worst way to explain it to people in person. And so we expect a certain, I'll give another example here. Yomu is rolling a standard die. Find the expected number of rolls she needs to get a 4 and then a 6 immediately after in that order. And so our states are this. Our states are really bad, like nothing. There's 4, and there's win. And you win like this. You have a 1/6 probability of returning, and you have a 4/6 probability of going back. Here you have a 1/6 probability of going, and a 5/6 probability of staying. And so our expected values are, let's call them E and F or something, right? And so E is, 5/6 E plus 1/6 F plus 1. And F is equal to 1/6 F plus 1/6 of 0, actually. When you get here, guess what? You get 0, so nothing. And then plus 4/6 E plus 1, and I'm dangerously close to some other stuff, so I'm going to erase it. Sorry if you really were enjoying the calculations there. I guess that's not good. But, right. And then there's these two equations. And what we want to find, of course, is E, which is this one. And so same thing, we get like, 5/6 F equals 4/6 E plus 1. We multiply by 6, divide by 5, you get E5 is E plus 6/5. Wow. And then this is a thing you can substitute back here and you get like E equals 5/6 E plus 2/15 E plus 1/5. You get like 1/6 E minus 2/15 E equals 1/5. And so these are both factors of 30. This is 1/30 E equals 1/5. And I believe E equals then 6. Never mind. There's a 1 here. See, this is why. Right. Don't make sillies, kids. This is 6/5. And so this is 36. There we go. 36. Okay. And this kind of makes sense, right? Like you said, like you need to get 2 specific things. There are 36 options of those, right? Like 1, 1, 4, 6, 4, 4, or something. Then, after 36 tries, you're sort of vaguely speaking expected to get it to work. Here's another one. I am not going to do calculations for this one as well because not because I think they're bad, but because I think they're like kind of not that cool. So this problem you may have seen. Some of you may have done this one. Again, I'm old, but I'm not so old that I'm doing problems that like none of you have ever done before. So maybe some of you have done this problem, but this is modified. I am doing the expected value problem because the probability one is a really, really abusive use of symmetry. I was originally going to put it where the SMT 2020 problem was, which would probably have been a good idea given how horrendously that went. And now I know that any problem that actually has a hard diagram, then I'm not going to be able to explain my idea very well. Anyways, we sort of, we want to find the expected number of jumps needed. Where we start here and we sort of random jump in any order. And the sequence ends when we get at any of the borders of the square. I remove the vertical condition. I don't really care about that because that just makes the problem harder. Right now, all I just care about is how long it takes for me to reach a side of the thing. And so actually I will do the math because it seems like it could be tamed maybe. And this is like, we will label the expected value here is E. This is like, I don't know, we'll call it C for corner. This is like, I don't know, like M for middle, okay? And I end up with E and M, C, E, M, and C. Interesting. Anyways, so E is 1/2 C plus 1/4 M plus 1. C is 1/2 E plus 1. Yeah, and then M is just E plus 1. So we can substitute all of these back. In fact, E is actually just going to instantly come out because we're going to get 1/4 E plus 1/2 plus 1/4 E plus 1/4 plus 1. And so that's E over 2 equals 7 over 4. So E is 7 over 2. So we expect to take 3.5 jumps. And I hope you all are familiar with expected value. I know that expected value is not necessarily the most intuitive subject. But, and I hope that y'all know what that is. Otherwise, I know I'm probably screaming at you and you were like, what the heck is he talking about? He is crazy. And well, I must sound a little bit crazy. Okay, one last example of states with EV, and then I don't know, maybe I'll go back to talking about cubic equations or something. I have a problem set down here, but I might go over 9. 9 I think is an interesting problem, but otherwise, not really. So this is a really, really weird states problem. You have like a snake, he's going around and taking, you know, parallel steps or something. And we want to know the first time that he sort of creates a little unit square, right? Like he goes this, something like this. Not necessarily this. Obviously, there's counterclockwise as well. And I will tell you that the easiest way to set up the states here, and this might be kind of confusing because you don't actually sort of know where you're going sometimes. You default, of course, have at least one side, right? You can't start with 0. In fact, the one side state, or like the state where like we only have one side that's usable, is if say we go like here and here, right? Then we cannot, like these two edges are not going to be part of the same square. So that means that basically everything before this is useless and all we have is one edge, right? Similarly, if we go forward and we go back, that's also bad, right? And maybe I should be reading the statement. This is a snake and he's going, yeah. I mean, I guess I already sort of explained the statement here. But basically, there's a snake, it's going in random, you know, +1, -1, up, down, random walk in the plane, however you want to talk about it. And so that's the first state. The first state is just really bad, right? And the next state is, okay, we have something. We have this, woohoo. And this is a state. And then the next state we have is this one, which is we have like a curvy thing, right? And then, of course, after that, we have a chance of winning, right? Which is to do boop, 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 or I don't know, something like this. It doesn't really matter. Again, when I say this, I don't just mean this. I mean, this also counts. This is a very liberal definition of like what this is, right? Okay. And I have 3 variables, and I'm going to call them like, I don't know, as A, B, and C here. I'm lazy and I don't have any better ideas. So A has a 1/2 chance of just doing something bad. Going forward and going back is bad. Going forward and going forward again doesn't help you either, right? And so you have a 1/2 chance of just going back, right? But you have a 1/2 chance of turning left or right, right? Like this. Then that's that. And then +1. B, if you start like this, same idea. You have a 1/4 chance of creating this thing. You have a sort of getting a turn, but you don't have one of these. You only have this, right? So you have a 1/4 chance of staying. Yeah, you always have the 1/2 chance of returning to A, going back or forward, which always is bad, and a 1/4 chance of going to C, right? And then +1. And finally, with C, you have a 1/4 chance of going back to B, a 1/2 chance of going back to A, and a 1/4 chance of winning and making a square. But you also have a +1 there because again, you're still taking steps. And now, after all of this, we're going to add all these together. We're going to solve the set of equations here. So first A equals B plus 2. Wow. Then B, so A equals B plus 2. This is B equals 1/4 B plus 1/2 of B plus 1 plus 1/4 C plus 1. And so after all of this, we get 1/4 B equals 1/4 C plus 2. So B equals C plus 8. Finally, when we do this, then we have C equals 1/4 C plus 8 plus 1/2 C plus 10 plus 1, a lot. And so that we get like 1/4 C equals 2 plus 5 plus 1. And so C equals 32. That makes sense. That seems right. 32 is a reasonably long number. It is about 1/24, which is sort of what you sort of expect to get. It's about 24. Yeah, there's that. That's this problem. The state said it was kind of unconventional, but it's not too bad, I think. And you can tell the difference between me teaching combo and me teaching geometry. I am more of a geometry person. Okay, problem set. I have 8 minutes left. I don't have much to talk about. I don't think I'm going to be able to do this problem very quickly. I will send the problem set, of course, somehow through the website, through Rich somehow. But you'll get this, and hopefully you'll be able to read my intended ideas a little bit better. Maybe I didn't make the handout a sort of comprehensive lecture, and then I managed to make the lecture not a comprehensive talk. But hopefully, from listening to me and reading this thing, then you'll have learned something, and that is a win in my book. Anyways, these problems, there again, like the one that I should have sent last time, they're supposed to be in difficulty order, so do not be surprised if like, oh, you cannot do all of them. They're not intended as a bucket list. They're intended as a set of problems for you to do. If you want practice beyond the confusing stuff I scribbled over here. Right. And so this problem, maybe I'll give a hint of the problem. I don't think I'm gonna be able to solve this problem like in the time that I have, but basically just like, this is like, there's so many symmetries here because there's like left-right symmetry. This is like, okay, the idea is that you take a same random lattice walk from the plane, right? You start here, and you go all over the place, right? And this is bad. This is good. I guess color. This is good. This is good. This is bad. This is bad. Good. This is good. Bad. Good. And that's a lot of states. You're thinking, even if I use symmetry, then that's a lot of states. And you would be right. But we are lucky that we can sort of do something here. First of all, this one, and well, maybe X might be proper, but maybe I'll use a color. Yeah, let's use a color. Okay. Orange again. This one and this one are the same, and this one are the same. They're symmetric. And then similarly, we can do the same thing for like, this one and this one are the same. This one and this one are the same. And then the other important leap of faith is that this is 1/2. Anything on the line x plus y equals 3 is 1/2. Because that's because the number of ways to get here is the same as the number of ways to get here. And sort of generally speaking, if you reflect over, then good turns to bad. And so the probability of good is equal to the probability of bad. And so then the probability of good is 1/2. Probability of bad is 1/2 as well. And after that, after all the simplifications, you have 3 states. You can do thingy. You can do states equation thingy, and then you can get the answer. Wow. Yeah. And so that's really this problem, the sketch of this problem. If you want to look at solutions or something, then for any of these problems, they should almost all be a place where you can easily find them. These are AMC problems, AIME problems. This problem is silly, and if you don't do it, if you can't get the answer, then like maybe you're overthinking it. This problem is also kind of standard, so I hope those don't talk to each other. But these are AIME questions. This is an HMMT question. You can find those on their website. This question is a question written by some of my friends, and so you may not be able to find it so easily, but you should probably be able to find it somewhere if you look on AOPS hard enough, or you can ask me. You may be able to have my email, and I will look for these for you. And yeah, and then one last thing. I talked about problems written by my friends. if you are at all interested in sort of taking AIME level competitions, then there's this contest here, Matt, written by a few of my friends. I didn't have any hand in the development of this one, but it's at this website, math.mathadvance.org. Maybe y'all are interested in that. And that's really just that. I don't want to hang too on this, but I think this is a good opportunity. I, again, did not really have the hand in the development of the contest, but I have seen the problems. And I have 4 minutes left, but I honestly don't have too much to say anymore. This lecture did not go as well as I expected it to, but hopefully you learned something. Hopefully I wasn't too annoying. And I will just hand it over to Rishio. Yep. Okay. Yep. And yeah.